So our Newton's second law is force equals mass times acceleration. And our force due to friction is always going to be our coefficient of friction, this letter that's the Greek letter mu, times normal force. Kinetic friction has a specific symbol, this mu with K as a subscript. And static friction, when something is not moving, is mu with an S. So if you ever see those two symbols, that's what they represent. So down here, we've got mu with a K, so that's kinetic friction. That's when something is moving. So the information that we're given in this first problem is we have a sled that weighs 300 newtons. So remember, we're not talking about the mass of the sled. We're talking about its weight or its force. Is moved at a constant speed. So constant speed is telling us that our acceleration is 0 meters per second squared. Over a horizontal floor by a force of 50 newtons applied parallel to the floor. First, construct a force diagram to the sled. So we have a horizontal floor, so that tells us that our axes are going to be horizontal axes and our vertical forces are going to be straight up and down. We're told that it has a weight of 300 newtons. So that's telling us about force due to gravity. So we've got Fg, and it equals minus 300 newtons. We know that normal forces, there's no push or pull that would be bringing this thing up or down, is going to be upward with the same magnitude. So 300 newtons. It's being pulled at a constant speed by a force of 50 newtons applied parallel to the floor. I'm going to have it moving to the right. So I'm going to call that my pull, and it's 50 newtons. I'm going to make that direction positive. And then we know that it has no acceleration. What does that tell us? If there's no acceleration, that tells us that our forces are balanced. And we have balanced forces, that means that our forward forces are the same magnitude as our backwards forces. So this pull forward is going to be equal to the friction backward. And the magnitude of that force is going to be 50 newtons. So that's going to be minus 50 newtons backwards. Those two are going to be equal in magnitude. So I'm going to put my equals marks there. So there's our force diagram. You guys have any questions about the force diagram? Yeah, now we know about balanced and unbalanced things. So both are fair game. The next question says, determine the coefficient of kinetic friction between the sled and the floor. Well, to figure that out, we're going to need to use our friction equation. So we know friction is equal to the coefficient of friction, so that's coefficient of kinetic friction, times our normal force. And we know both the amount of friction force and normal force, so we can figure out this coefficient. So we got friction divided by normal force. Our force of friction is going to be 50 newtons. I put minus 50 newtons because it's backwards. Normal force is going to be 300 newtons. And so my total value there is going to be, it's good, minus 0.16. The negative is just telling us about direction. This is just telling us that our friction force is going to be backwards. So generally, coefficients of friction are reported as plus or minus. And you'll notice that there's no units that go with it. One clue is that it's a coefficient. So coefficients don't normally have units. The other is that the units are going to completely cancel out when you do this calculation. So you're just left with a number. Next it asks, what would the acceleration of the sled be if the coefficient of kinetic friction was 0? Well, what would be the result of that? If we had a coefficient of kinetic friction that was 0, that would mean in our equation, where we were multiplying this times normal force, we would end up saying, well, our coefficient of kinetic friction is 0. When we multiply that by our 300 newtons of normal force, we end up with friction equaling 0 newtons, right? So it would say there is no frictional force. If that were the case, then we would have a net horizontal force of 50 newtons. Do you guys see how that is? Because our net force is going to be the sum of our horizontal forces. So that's going to be friction plus pull. And if what we need to do is solve for acceleration, when we add these two together, because friction would be 0 newtons, our pull is 50 newtons. That's equal to our mass. Ooh, what's our mass of our object? If we take a look at our force due to gravity here, and it's 300, we know that that's the mass times the acceleration. So what we need to do is divide that by our minus 10 meters per second squared to get our mass. So our mass here is going to be 30 kilograms. So this is going to be equal to 30 kilograms times our acceleration, the thing we're solving for. So what we need to do is divide both sides by our 30 kilograms. And what we find then is that going to be 1.6. Yeah. So for an acceleration, I got 1.67 meters per second squared. So it'd be a lot of acceleration. And that's the difference between having something where you've got some traction and not having traction, right? That's the difference between a road where your tires have some grip and a road that's covered with ice where you can't get any traction, right? And then you'll accelerate, you speed, you might end up where you don't want to be. All right, so what questions do you guys have about that problem? Does it all look pretty familiar? It's just put together a little bit different way. So what I want you guys to do with the rest of the period is just work on that worksheet. So we've got an Atwood's machine for problem number 2. So remember, when you draw the force diagram, it may help you to straighten this out a little bit. And so to think about it, instead of being up on a table, to think about it as a system where your force due to gravity is going to actually be pulling both of those blocks in that direction. And over here, we'll have another gravity and normal force. And so that might be, just remember that that's the case for Atwood's machine. Again, we've got kinetic friction down here, so you need to use the friction equation again. There's a, oh, these are fun. There's a tile floor problem. There's a book that's being held up against a wall and a ramp. So there's a couple there. It's okay with you, it's all right with me if you guys work together on those. If you have any questions, please let me know. Let's see if we can get all this done in class today. We'll see how close we can get. All right? Sound good? Okay, you guys can go ahead and get started.